怎么在这个了？我记得原来在这个。看着我，就哪个是2D 哈？不对呀、
我来说。
你现在全变了，都不一样，你弄。PPT 考进来了。
PPT 已经考了。
我有，改一下名字，改一下尾，你改名字，改一下 rename， 改不了，要 co-host 也行 ，make host， 改名字 ，rename。
不知道为什么。
重新，这个怎么改？改不了。全了。他账的时候不是可以写名字的吗？在这儿改。行，可以了。然后怎么招呢？8276416，2584，2584。把那个 slides 打开 PPT， 对不对？
就在这。
不用管了，你把那 PPT 打开。
PPT 已经打开了。
OK。
7、8、9、10。
哎，我看我怎么用这个白板哈，等一下我看看。现在有点新版本了 ，share 不了。完了 host 还是不行。
改一下。
不视频了。行了，我试试。可以，行，可以。啊，哎好。Okay, so we can get started now. So last week we discussed the Gaussian channel and we introduced the entropy definition, which is a little bit different from the entropy for the discrete random variable. And then we also talk about the parallel Gaussian channels and derive the water filling solution. So I would like to give a quick review what we learned last week. I'll skip this definition so we can go to the Gaussian channel directly. So Gaussian channel is a typical model of the signal transmission over the AWGN channel. So that means the channel is corrupted by the wide Gaussian noise. But you may wonder where is feeding. We may consider later. Because firstly, Gaussian is typical and simple. We only have the Gaussian PDF. Once you add the feeding effect on this channel, so that will be complicated. For example, you will have y equal hx plus z, and h is Rayleigh distributed. So you will have Rayleigh distribution and Gaussian distributed noise. So that will make the whole problem more complicated. So that's why in the beginning we start from a simple example. We ignore the feeding effect. We just start investigating the effect of the Gaussian noise on the channel capacity. So that's why we consider the Gaussian channel model. And then the capacity of the Gaussian channel is defined as the maximum of information theory, the mutual information between X and Y. So, and also the Shannon derived this major result in 1948 in his pioneering paper. So we also give quick review of root proof. For example, we want to transmit X through the AWG channel, and receiver we get the signal Y. And then the mutual information between input and output X and Y is given by this formula, if you still remember, right? So that is the chain rule for the mutual information. And also we know that the Z here is a Gaussian noise. Then for a given X, then Y is only Gaussian distributed because X is given, and then Y equal X plus Z. So Y is also Gaussian distributed. And then we can say the distribution of Y is the same as distribution of Z for a given X because the X is constant for a given condition. And the entropy will be the same because here we have the first property. You see the entropy of X shifted by a constant C, it does not change the entropy information. So here it's just, so that's why we have the X plus noise. So the X here is a constant. So then that is the entropy is still the same as the entropy of the noise. And this from the example 1, we know that for the Gaussian distribution, the entropy is given by this result related to the variance. You see the theorem 1, example 1 here on the page 5. Let me see. Example 2 on page 6. So that is the entropy of the Gaussian distributed random variable. So the result is related to the sigma square. That is the variance. So here we use this result. And then we can solve this second item. For the first item, so the entropy of Y. And we know that if X is not known, so that Y equal X plus noise, then we don't know the distribution of Y because you don't know the distribution of X, right? So in this case, we cannot calculate exact value of the entropy of Y because we don't know the distribution, okay? So but here, we can get upper bound value. That means although we don't know the exact value, we could derive that this value cannot be larger than a bound. This is called upper bound. What's the meaning of that upper bound? It means that the maximum possible value. So that means the entropy of Y could not be larger than this value. What's the meaning of this value? So we could also get this result from this property 4 of theorem 2. So that means for any X with arbitrary PDF, that means we do not specify X must be Gaussian. It could be any distribution. Then in this case, the entropy of X cannot be larger than this value. So this value is not random. This value comes from some result. If we go back to the theorem 1, we will say this result is that the same as this one. If you look at equation 5, the Gaussian distributed random variables x1 to xn, their joint entropy is equal to this value, you see? And you come back to here, you say exactly the same. So in other words, for multiple random variable, no matter it is 1 dimension, 2 dimension, or n dimension, the joint entropy value cannot be larger than the entropy values of the multiple Gaussian distributed random variables. So in other words, Gaussian distributed random variables can maximize that entropy information. Because this one is just the right-hand side is exactly the same as the entropy value of the Gaussian distributed random variables x1, x2 to xn, if the both sides have the same covariance matrix. Okay. So in brief, I mean that you could ignore the equation, but in brief, you should understand this concept that only the Gaussian distributed random variables can maximize the hx or hy. That means the entropy. Okay. In this case, we come back to this exam question. The hy, although we don't know the distribution of y, we say that this entropy value cannot be larger than the entropy of the Gaussian random variables. And its covariance here is the p plus noise, because the variance of y, you could calculate the variance of y equals variance of x plus noise. That's equal to the variance x plus a variance of noise. That is p plus n. So that's why we have this inequality on the right-hand side. If we put back into the equation 14, so we can get the answer of 15. So that's why we can have this smaller than or equal. So that means the mutual information cannot be larger than the half of log 1 plus p over n. P over n is also called signal to noise ratio, SNR. So that means maximum result will be equal because the capacity C is defined as the maximum of result of mutual information. So that's why C is equal to the half of log 1 plus SNR. So we, for that's only for one channel, for one, like this one, for one channel with noise on. Okay, so how about the multiple channels in parallel together? If you look at this parallel channel, everyone can be viewed as the Gaussian channel, averaging channel. You transmit the xi through crossed by the noise zi. You got the signal at receiver as a yi, for example here. They are not totally independent of each other because their transmission power is connected to each other. That means they use the same total power. It's the same meaning that is, okay, although we have the 100 or 10 different channels, however, the total power of the transmission part is the same. So that means if you allocate too much power in the channel 1, you will have the less power for the other channels. So that is a constraint, okay? So due to that constraint, so those channels are connected to each other for the power allocation, okay? So that means for these parallel Gaussian channels, then the question is how we could allocate the power among these different channels optimizely. That means smartly, because you don't want to waste the power, right? You want to allocate power to the channel, and then so that in the end, you could maximize this channel capacity, right? For example, if this channel is very weak, that means capacity is very low, the value, and also you want to allocate too much power, but it does not help because the noise is too huge. So if you allocate too much power to that very noisy channel, it does not help on one hand. The other hand, you have less power for the useful channels. So then that's not a good solution. Then what is the best solution, right? For example, you are given 10 different channels, and you have, for each channel, they have different noise power, noise level, and then how you have a total power of the signal transmission that is, for example, 10 watt. So how do you allocate the power? So that is the problem. So then we model this problem as like this one. As this one, we want to maximize the mutual information between the input and output. Here, input is not a single x. The input here is a block of x, x1, x2 to xk, because you have k parallel channels. And also you have the k output, right? It's like a vector of input, a vector of output. And the total power here, you can see here, that the summation of xi square and smaller than p. It means that the total power is constrained to the total power constraint, okay? And for each power, for power pi or pj for each channel, so we had p1, p2 to pk, they are the variables. We don't know exact values. So that's the variable we want to optimize. We want to determine that is what is the best solution for this power allocation. So that is optimization problem. So we got the objective function to maximize the capacity. We got the constraint function, that is the power allocation constraint. And we got the variables for the optimization, that is P1, P2 to Pk. So this is a typical optimization problem. So you have object, you have constraint, you have the variable to optimize, then the left is just to solve this optimization problem. Although you say we got the objective function, it still looks very complicated, right? Look at the 19. So then we derive step by step. After that, we got the equation 20. And we can see this is just the summation I and the Ci. So for each one, it's just the single channel capacity. So the only different line in that for each channel, you have different power Pi, you have different noise power Ni, okay? So then we replace this equation 19 by the equation 20 because it's the same, okay? So that means we want to maximize this sum C, sum Ci, subject to the Pi equal P. You see, this is the problem 21 to 22 are quite simple, right? So at least in terms of expression, very simple. We want to maximize the sum Ci subject to the Pi equal P. And then we can solve this optimization problem by using the Lagrange multiplier method. We talked about that last week. So the solution goes by this. Mathematically, we can get this power equals the new here is called a constant that could be solved through this equation because you know the node power for each channel, you know N1, N2 to Nk, you know the total power so that you can know the constant nu from this single equation. Once you know this value of nu, you put it into equation 23, you could get the power for each channel. So that means that this is a mathematical solution, but we also talk about the physical meaning of this mathematical solution. So you can imagine that is the power allocation is just like the water filling. So you have, in the beginning, without any water filling in, so it's like the swimming pool. You have the different lanes, and each lane may have different height in terms of the floor, right? So this is the lane 3 that has a very high level of the floor, and this is a middle one, and this is a deep one. So when you fill the water into this swimming pool, the water goes to the lane 2 first because it is very deep, right? And then once the water level rise to somewhere here, so then the water will also go to both lane 1 and lane 2 together, right? And also you can imagine once the water level rise again, so then the water may also go to the lane 3, but it depends on the total the water volume, right? So for here, you see the total power P1 P2 equal to P, so then that is stops because the water cannot rise again because the total power has been used up. The P1 plus P2 has been equal to P already. So you cannot go up. It means that the P3 will be 0 because there's no water fit into the lane 3. It means that this power allocation for the channel 3 is 0. And also for the channel 1, you got the power allocation P1, channel 2, you got the power allocation P2. Compared to this one, you see P1 equal to nu minus N1. This is nu here. Nu is the water level. Nu minus N1, that's P1. Nu minus N2, that's P2, right? And also P1 plus P2 is P, the total power. So that gives a very intuitive illustration how this optimization solution gives the meaning. So essentially, from this figure, you can conclude that is the power allocation for the best one is that you always give the more power to a better channel, which has less noise, right? Look at this one. N2 has the least noise power, so it gets the most signal power. And this one is also middle, the noise one, channel 1 is a medium level, so you give the P1 here. So I think that is the intuitive correctly, because you always want to give the best resource to the best capable channel, right? Then it will maximize the total channel capacity. And then mathematically, we also have proved this is correct. So this is the water filling solution. And this one actually, I think next week, probably next week, but today we are going to talk about the MIMO and spin-up coding. Next week, that is week 10, we will also study the OFDM and the MIMO FDM. For the OFDM, I think that some of students have already given the presentation in OFDM systems in week 3, 4 around. Then the OFDM actually is the example of the parallel Gaussian channel. Look at this one. For the OFDM system, you have the number of the subcarriers, probably 2,448 subcarrier or 64 subcarrier based on different wireless standards. And for each subcarrier, you also need to study how much power you need to allocate. So that is that's called the power allocation for the OFDM system. There are a lot of work to do this. Actually, many research papers published to investigate the resource allocation for the OFDM. In that context, power is one of the resource. Also, we also consider other resource. Not only power, we also consider the rate. How we can also allocate a different rate, or we can allocate different to the bit. For example, how many bits we can allocate to this channel, and also we can bundle different subcarrier in one group. Also, we could, if we consider multiple users, then we also allocate this resource to the different users to keep the user fairness. Because here we only consider one transmitter and one receiver, so that's one-to-one. But in the communication system, we may consider the multiple user. For example, here we have the AP access point, and many students want to access the Wi-Fi. Then you altogether will compete for the resources, right? Because only one transmitter over there, AP, broadcasts the signal to all of you. And then you want to access the data and access the channel. So actually you work in the competitive base to access that Wi-Fi. Then how we can make sure then no one is left. So that means we need to keep the user fairness. So that means in that scenario, the multi-user OFDM system also is another advanced version of this parallel Gaussian channel. So a lot of research papers have been published to investigate different version or alternative of the parallel Gaussian channels. But here, this is a very, very basic example, okay? So that is the Gaussian we studied last week. And also we talked about the MIMO last week. Not all of them. We reviewed the concept, but we have not derived the capacity. We only show the channel capacity of the MIMO channel. But today, we are ready to prove that. And also, we are going to introduce different the capacity definition for the MIMO systems. And also, today, we also got planned to further study the spectrum coding. And then, although you say the lecture note is lecture 10, but we still have the lecture note 11 for the next week for the OFDM. The reason that we got so large number of students enrolled in this course this semester, we got 130, 140 students. It's almost double the size of the last year. So that's why we allocated one more week to the presentation. So, but I don't want to lose some of the lecture contents or squeeze or compress. So that's why I still want to include the OFDM topics into this course. So that's why in the last 2 weeks we speed up a bit, right? If you attend the class or you watch the lecture recording, you may say we speed up the lecture a little bit, right? Almost a half class, so that we can keep all the planned contents of this lecture. Okay, for the MIMO, let us see here. This is the MIMO channel. Last week we talked about that. We have a transmitter with multiple antennas, a receiver with multiple antennas. Some students may wonder, that's realistic? Do we have such MIMO systems in practical life? Yes. If you notice that some base station tower on top of the building, even on our campus, on different buildings, you look at the top, there is like the small version of the base station. It's not like a TV tower. It's like just like a panel, a white box. Inside the white box, it's actually the antenna arrays. It had the 4G, base station and 5G base stations. So it started a white box, and it may have the different tilt angle, 3 angle for the 3 sector areas. On top of the building on campus, you may notice that. So, and for the Wi-Fi, also we have already the MIMO Wi-Fi. I'm not quite sure if you bought in your home. If you go to the market, you say, I want to buy the high-speed Wi-Fi. So you already got at least 2 antenna or 4 antenna or even more antennas. There are many commercialized product of the MIMO so far. 10 years ago, probably not too many, but now it's already the mature product. Okay, that's MIMO. And because this is a 4G and a 5G version, for the next G, we consider the 5G advanced or 6G by 2030. So what is that possible MIMO? So in their future, that MIMO may be equivalent with hundreds or thousands of elements of the MIMO. So that the antenna will be smaller, but you may integrate hundreds or thousands of the antenna elements together in a panel, in a cylinder. So then that MIMO would be called a massive MIMO, or very large MIMO. Okay. But basically, the signal transmission model can be depicted in this figure. We have a transmitter with multiple antennas, and all these antennas transmit the signals, S1, S2 to SM, respectively. At the same time, we have the multiple antenna as a receiver, and each antenna gets the signals from all the transmitted signals together. And yeah, that means, yes, these signals will interfere each other and arrive at one antenna at the same time. So that means you will, for example, you want to get the signal from the X1, at the same time, you get the interference from X2, X3 to XM, because they transmit at the same time. At your receiver side, you got the combined version. So that's why last week we derived this equation, remember? So for the Y1, you got the H11X1 plus H12X2 plus H13X3, etc. So that means each received signal includes all the transmitted signal together, right? Although they include different the channel coefficient. So it's not easy to extract the signal X1 only because you got so many interferences. And the same, the like one, the Y2 also got the different the interference together, so that the equation 5 that we rewrite the equation at a vector. So Y here vector is given by a matrix H, and the signal vector X, and the noise vector, and the signal and the channel here H. You can see that is it's the square, not square. It's like the rectangle matrix with n rows and m columns. So that depends on the number of antennas you use, right? N antenna as a receiver and m antenna as a transmitter. And if you look at the channel coefficient for this matrix, so the channel coefficient usually is a complex number and random, because we consider that the rate is defeating, and each channel coefficient is modeled by a complex Gaussian random variables. So it, in other words, Hij, the element, is generally a fading coefficient. It is a complex Gaussian. So that means in the matter simulation, if you say I want to simulate the MIMO signal transmission, I want to simulate equation 5, so you need to create two random things. First, you need to create a random noise, right? The noise is random, and also follow the Gaussian distribution with zero mean, but some variance sigma square. So then what is that variance? So that depends on the SNR, signal to noise ratio. For example, you say, okay, in the current scenario, SNR is 10 dB. So if the signal power is 1, so then you can say the noise power should also be about the 0.1, right? So 1 over by 0.1, that would be 10. So then that would be 10, is that 10 dB? That is 1 dB. 10 That is 10 dB, yes, correct. So that means the noise variance depends on the SNR that is given. So why I want to mention this sentence? Because I received some email regarding the project. Some students ask, okay, for some project you do not give us the information of the noise. So how do we know the noise power? I don't know, because without that noise power or variance, we don't know how to generate the noise samples in the MATLAB, right? But I say that if you read the question, you are asked that you need to plot a curve of something in terms of the SNR from 0 dB to 10 dB, for example. So that means you first need to specify a value of SNR, signal to noise ratio. Once you specify that, the context, SNR, and then you will know the noise power and the variance, and then you can do the simulation. And next, you can change another value of SNR, for example, from 0 dB to the 5 dB, then the noise power is changed, so that you can get 5 dB, right? So that means noise power is usually limited at 1. You fix the signal power as 1, and you change the noise power accordingly for given SNR value, so that you can know the noise power, okay? So that is the simulation for the project details. Again here, for the equation 4 or equation 5, you see there are two random things. One is noise, the other one is channel, H. H is radial fading. That means each channel coefficient, Hij, could be also complex Gaussian. That means very similar to the noise. That means you also need to simulate the channel from I to J, and then following complex Gaussian distributed. But good thing that currently we only, I remember we are somewhere in theorem 2 we only consider a fixed value. That means we do not want to complicate the problem. We give the very simple assumption. That means H, okay, forgot the fading. We do not say the fading. Originally we set up this fading. That's a general case, but we don't want to touch the fading in the beginning. That is too challenging. So we say, okay, how about we start from simple example? How about the channel is constant? Okay, that means this channel equivalent Hij are all fixed constants, no fading. Okay, this is simple. And then let us say what happened. Once we know that scenario, and then we can move forward to say how about we consider the channel Hij is fading. Okay. For this one, we consider H as constant. Then the only variable is noise. The noise is Gaussian distributed. For this case, okay, for a given channel and the noise, this is signal power, there are signal input covariance matrix Rx, and also total power constraint is P is given. So the capacitor MIMO, that means the equation 5. So for this channel between vector X and input vector Y, so what is that channel capacity? So capacity formula is given by equation 6. So that's the result. We are going to prove it, okay? But still here, we can have a look first, and then before we go to the detail for the proof. If you look at the equation 6 here, you see that, okay, this is the maximum mutual information, right? Should be like that. But the mutual information here is not of simple form. It's like the log with determinant, right? This is like the determinant. Determinant of a matrix. Inside of determinant, you got a matrix, the identity, plus 1 over sigma square, that is the signal to noise ratio, right? If you consider signal power is 1, noise power is sigma square, that is SNR. H here is constant, right? We can ignore because it's just constant matrix. Rx here is covariance matrix. That is depending on the input signal distribution. And also the H, superscript H, that means called Hermitian. Hermitian operation means that the two-step. Firstly, complex conjugate. Firstly, the complex conjugate. Secondly, transpose. Okay, that's called the Hermitian. For example, you have a matrix. You firstly take the complex conjugate, and for example, A plus Bj, you can change to the A minus Bj, right? If it is A, it's still A because there's no imaginary part. So then you take the transpose. Transpose, you know the matrix, row become to column, column become to rows. So that is the operation of the Hermitian. So now I have already explained the physical meaning, and then let's see how we can get this formula. Again, we start from the beginning. The capacity is given by the maximum mutual information between x and y. Okay, so that is the input vector and the output vector. And also the mutual information given by the hy minus hy given x. Okay, that's nothing new here. Very similar to what we did for the single channel, right? The only difference here that we have the both phase, x and y. If you look at the previous example, I could not, that is the last week. Let me see here. Yeah, look at this one, mutual information given by hy minus hy given x. We can put side by side so that we can see the difference. You see here that on the right hand side, that is for the single, for the Gaussian channel, we have the one symbol input, one symbol output. There's no vector, right? It's only one element. So the mutual information is given by hy minus hy given x. But here on the left hand side, we consider a vector because we consider that the MIMO system is like the vector input, right? That's the only difference. Again, because h is given, here is that is x is given, right? So we can consider like this one because h is given. That's assumption. That's a condition. So h given, we put a condition. That is y over h given h minus y given x and h. Because previously the y given x means that condition x, but now we have two conditions, x and both x and h. Okay. Next, we calculate the second term, y given for given x and h. If x and h are both given, if you go back to the equation 5, okay, hx is given, so this means the whole thing is given, right? It's like the constant. Hx is constant. Although it's a vector, it's still constant because it's given. Both are given. Then the distribution y will be the also Gaussian distribution, right? And the same, similar to the noise. So the entropy of y is the same entropy of the n. So that's why here you see this one, the entropy is the same of the entropy of the noise vector because x and h are both constant. So that's also, let me see, I want to make the comparison of what we studied for this one, for the single input channel. Here you see y given x is same as y, the h of z, because x is given, then the entropy of y is the same entropy of the noise, right? So the entropy of the noise only here. So it's the same here is the entropy of noise only. Okay. For the entropy of noise, but it is a vector, so we can still get this result. So for the, I think we have result here for the node vector. So we have the node vector, the entropy is given by this result. We can get the answer here. And then we come back to say the first term. So how about y, the entropy of y given h? Okay, so that is the question because if you look at equation 5, y equal hx plus noise, if h is given, but you don't know the distribution of x. If you don't know the distribution of x, you will not know the distribution of y, and you cannot specify the entropy, right? So that's still challenge. Very similar to the story here, right? So in this case, we can use the upper bound. That means that the entropy of y will be smaller than or equal to the entropy of the Gaussian distributed random variable. So that means the entropy here, we don't know the distribution, we don't know the exact value, but we say this can be maximized when y is a Gaussian. If y is Gaussian, that is very similar to like the smaller than or this value, right? So then we consider how about y is Gaussian? Then we want to maximize this first term value. So in this case, y given h, because y is already Gaussian, so we will know the capacity value, the entropy value from also the same equation 3. So but we use different variance. The variance here is the variance y, so we can get this answer. And the covariance of y here, you can calculate it step by step because y equal hx plus noise. You can substitute in there, hx plus noise times, it's a Hermitian, so then this end, this gives this value. So then we substitute this value into this equation and then into this top equation together, so you will get exact answer of this value. Okay, so that means the maximum mutual information is given by this determinant, especially this is called a determinant, determinant of this matrix. But here you also consider different examples. For example, that how about one dimension? If one dimension, you will say, okay, this is n will be 1, so this will be 1 plus 1 over sigma square. H here, because only one channel, you can consider each just H or 1. And then Rx here is just the signal power, that is just the P, and the times 1. That would be 1 plus P over sigma square. So it's the same as this one, right? Like this one. You may wonder, what is half? This is not half. Because here we consider the complex Gaussian. This is only for real. This is only real part. But this one, we have the both in phase and quadrature component. That means we consider the signal is complex. That means it has 2 dimensions. Because, for example, QPSK, QAM signals, they are all the complex signals. So that's why we have this is a log 1 plus SNR. Okay. So that is capacity. So another technique is that called the parallel decomposition. I can show you what's meaning of this. So the main purpose of this decomposition is to diagonalization of the channel. Look at this one. This channel looks like the very complicated, right? Because each signal called interfering to other signals, and it's not clear in terms of transformation. So how about we can generate a channel which I can use whiteboard to show you what do we want to do. I can still keep the lecture note side by side. Let me see here. Let me draw here. SVD, for example, here we got 2 channels. This is a receiver, this is a transmitter. Very simple version, okay? So we say we got the signal like this form. We have the 2 by 2. That means 2 transmitter antennas, 2 receiver antennas. And then you say the signal is corrupted for each other, right? Interfere each other. So how can we make it like this one? Can we do like this? So if we can get a signal that is like the beam signal, so that means X1 only come to the receiver antenna 1, and the signal S2 only to the receiver antenna 2. So that would be very clean version, right? It seems that it's like the 2 light beam, they do not interfere each other. So that would be very good signal transmission because you don't need to worry about the interference. So then how we can convert it to this channel? So that is, we use a method called SVD. So mathematically, that could be converted. So that means in the beginning you say, okay, X1, X2, you cannot separate each other because for each one interfered by the other one. But in the end, you can see here, this one will be Y1 equal X1 plus noise, Y1, Y2 equals X2 plus noise 2, right? So this is noise 2. So basically you can write like this one, Y1, Y2 equal, can you see that? Yeah. The X1, X2, and plus, let me see, V plus the noise 1, noise 2. You see the same, right? That is H1, look at the right hand side, H1, H2 equal the diagonal matrix X1. Actually, you don't need to put a diagonal matrix. If we have the channel coefficient, yeah, we can add a coefficient, H1, H2. In that case, that would be, let me see, I'll show you. H1, H2, X1, X2. Like this one, right? So you have the Y1 equal H1, X1 plus noise 1, Y2 equal H2, X2 plus noise 2. That could be written as a vector Y1, Y2 as a matrix H1, H2. H1, H2 is a diagonal matrix, and X1, X2 plus noise 1, noise 2, right? So that means this channel called a diagonal channel. Diagonal channel. That means it has only elements on the main diagonal. For all other places, it's 0. So that's called diagonal matrix. But if you look at this one, this is channel coefficient. That if you can still remember, it's given by here. I do not need to write. Let's give equation 4. You see? That is y1, y2 equal h11, h12, h21, h22, and x1, x2 plus n1, n2. Right, so that is, if you look at the channel coefficient, it's 2 by 2 matrix here. And none of them is 0. So that's the reason at receiver you got interference from other signals. Because the H1 to H21, that's all diagonal, is not 0. So that's why when you want to get X1, you also get X2 at the same time, right? So that's called interference. So how we can change this channel to this one, right? If we have a 2 by 2 matrix, how can we convert the 2 by 2 channel matrix into a diagonal matrix? If it's possible, then result you can see there's no interference because y1 equal h1 xi, x1 plus noise. There's no x2. y2 equals h2 x2 plus noise. There's no x1. So they are separated from each other due to that diagonal channel. So that's the difference. You see, this is a diagonal channel. What happened? This diagonal channel plays the key thing. That means if you can get the diagonal channel, then you can make the interference free, right? Then how we can do that? So that comes to a basic mathematical problem. For a given, I can add another page to talk about this. Let me see. Yeah. So for a given, how does it work? Wait, let me see. Yes. For any given channel, I don't know what happened. Okay. Let me redo it. Cannot delete this one. Let me try again. Smart drawing, not smart drawing. Let me see. Add another page. Okay. So if we have any matrix, for example, we want to get B1, B2, 0. So that means any matrix, this is a simple example. If we have a 2 by 2 matrix, we want to make the 2 by 2 matrix into a diagonal matrix. So we need to do some transformation, right? How we can do that? So actually there are many transforms of the matrix. Right? One is like called, you may have heard of some of them, like the QR decomposition, like the SVD decomposition, like the LT transform. There are many, many different metrics manipulation. Either you left multiply or right multiply something. So SVD here means that for any matrix, if we say this is a matrix like the A, we can always multiply this matrix with U and V Hermitian to get a B matrix, which is diagonal, like this one. The A is any matrix. So that means you can always find two matrices. One is U matrix, that one is called V matrix. For any matrix A, you can always find matrix U and V such that U times A times V Hermitian equals diagonal. Okay, so that is called SVD, decomposition. So we don't, let me go to the page to show you that page. Yes. SVD. Let us see, singular value decomposition. That means for any, you can say for any matrix, it may be square matrix, maybe rectangle matrix, M times N, maybe complex, maybe real M. It can be factorized like the U lambda V Hermitian. That means opposite, right? So that means you could, that means this matrix can be written as that one. Or for this one, you could also multiply on the left-hand side U Hermitian, right-hand side by the V, that you will get the diagonal. So you could call the unitary matrix, and lambda here is a diagonal matrix, and V here is also the unitary matrix here. This is a unitary matrix. You may say, what's the meaning of unitary matrix? Unitary matrix have this property. That means U times itself, Hermitian, or equals identity. That's called a unitary matrix. Okay, it's a fundamental matrix property. So that means for any matrix, you can always find this UV matrices. So look at this is the form. You see this is the general form. Then it can be written as U times the diagonal and V here. And each column vector is unitary. And here you see lambda is all the diagonal and have 0 on the of the main diagonal given by this form. Okay. So U, because it's identity, it's the unitary matrix, U times U Hermitian is identity, V times V Hermitian is identity. So that is the meaning of the SVD. Okay. So this is the meaning of that. So here, I said that is, I could rewrite that, but is also, let me see, I'll rewrite this equation to keep consistent. U times V Hermitian. That will be consistent with this one, correct? That means for any matrix could be written, but we want to get B. So in other words, U Hermitian times A times V equals B. That is diagonal. Can you see that? Because on the first equation, you left multiply U Hermitian, you get U Hermitian A. And then on the right hand side, U Hermitian times U, that is identity. And then you multiply the V on the right hand side of A. Then on the right equation, you get the V on the right hand side. V Hermitian times V is identity. So you got identity times B times identity is still B. So that's why you got this step. Okay. So that means for any matrix, we can find this one. So then now we can go back to the original question. Can we find, why, let me see. Okay, so for this, firstly we have this monochannel matrix. Can we find something to diagonalize this channel? Yes, you can do that. So that means for this matrix, if you call this as H, you can always, by using SVD, I use different color to highlight. That means for the channel matrix H, you can always find U and lambda and V Hermitian. That means this is called SVD, right? H is the 2 by 2 matrix, and then you can always find U and V so that you can get the lambda, and this is the lambda. Okay, so you could always find this one by the matrix. You may wonder how I can find this U and V. Manually, it's not clear. I cannot do that. You don't need to do that. In the MATLAB, you can just type SVD, simple. Just say SVD of Hermitian, of matrix. That's it. Then the result you will get the U and V matrix. Right? It's a standard standard computation, so you can get the U and V. So now the question is that even you got a U and V, how I can make it possible to get a diagonal channel? So that's a step. We first say, okay, we can do the U and the V to get the to get the lambda, but then the question is how we can get this model. So you need to do something carefully. So here there are two steps. Firstly, at the transmitter side, let me go to the transmitter side here. That means you cannot transmit this thing. You need to add a vector V. Let me write. You need to add a V here before the transmission. That means here that is X. Previously you transmit X directly from different antenna, but now before that transmission, okay, do some matrix multiplication. You have the X vector, right? X1, X2. So firstly, multiply V with X. So that means here is you transmit V and X. You do not transmit X. You transmit V and X. If X is given by two elements, X1, X2, so V is a 2 by 2 matrix. So this is 2 by 1 vector, right? This is 2 by 2 matrix. So that means you need to multiply this signal, X1, X2, by a vector V. What's V? V is obtained from the SVD of the H. And the receiver side, you also need to add another block called U Hermitian so that you can get Y. So look at this, it's called receiver shaping. You may wonder why I need to add this additional block. Because remember that in original model without a U and a V, if you look at this one, the first MIMO on the top, so the model, if you still remember, that is given by the original is Y equal HX plus noise, right? Without SVD, before adding this any block. So now you say, if I get the V to replace Vx, replace X, that means I transmit Vx, not X, because I add a block called the precoding, V. I transmit X, so I can get Y. And at the receiver, I add another block, the U Hermitian times Y. So that means, okay, another block, this one, this U Hermitian H Vx, so this V plus U Hermitian noise. So look at this term. So this one, this is the output. This one is given by the lambda owner. Very simple one. Because, can you see? Yes, let me move up. Yes. You say this one, U Hermitian HV, that's equal to the lambda. That would be lambda x plus noise. So you make this channel to be diagonal only in the end. At the receiver, you got the multiple receiver signal, and you transmit X1, Y2, and the diagonal is only the main diagonal elements on the channel plus equivalent noise. So you make this channel to be a diagonal. So that is the equation 7. So diagonal means that you can separate signal one by one. Y1 equals the lambda 1 plus multiply x1, y2 equals the lambda 2 times x2. So lambda 1 and lambda 2 are called the singular value of the diagonal matrix. And you may wonder, what's the singular value? So that's also given, let me see, do here. Singular value, I think it's given somewhere, this one. So that means in the diagonal matrix lambda, that is this lambda is a square diagonal size, and actually this is lambda is given by the singular value. So it can also be the derived singular value given by here. So this is called the singular value. Can be also mathematically computed. So this is by the MATLAB you can do everything. That means in top SVD of the n matrix, you will be given the H, you will be given V, you will be given the singular value in the main diagonal form. So actually this is a standard process for the matrix. So we just use this property for our parallel decomposition MIMO channels. So I want to stop here for a break so you can digest the content. Okay, we take a break. Okay, just now we talked about the parallel decomposition of memory channel. We said in order to decompose this channel into parallel channel, we need to use SVD mathematically, but practically, it means that we need to use transmitter precoding V at the transmitter side and the receiver shaping at the receiver side. Overall, together, you will get the channel U, Hermitian, H, and V. Originally, it's only H, but now you got the U, Hermitian, H, and V all together. That will be the diagonal channel. So that is lambda, okay, for the parallel Gaussian channels. So, but if you want to do this, I'm not sure if you understand that how we can make it possible, right? You say that in the transmitter side, you want to apply the precoding vector V. The question is how you know the channel coefficient in the transmitter side, right? Because as you look at the precoding vector V, a matrix V, V is a part of H. Look at that first equation, right? Without knowledge of H, you cannot get V. So in other words, if you want to do the precoding by using V, you have to know the channel state information of H, CSI, at the transmitter side. Is that right? So that means you need to know the channel before the transmission. That means in the transmitter side, I want to add a precoding matrix V. V depends on channel. So it means that before transmission, you need to know the channel, state information, CSI. So that is a challenge for wireless communication systems. So then before your transmission of data, you have to know the channel information. And then you apply the precoding vector V, and then you transmit X, and then Vx through antenna. So that's it, right? So that means the critical challenge is that you need to get the channel information at transmitter side. Then we have to talk about some story about this. So you know that the channel information is between the transmitter and the receiver, right? Like this one. That's the channel, right, between transmitter and receiver. We assume that, okay, H is known. But if in practical world, you cannot just say, we assume it is known, okay? That is not possible, right? So you say, okay, I assume I'm a billionaire. It does not work, right? So you have to think about some way that, okay, how you get the channel information. For this one, you transmit data to a receiver. You say channel is known. No, before that, you have to be clear how you could know that channel information. I can tell you one method. One method is that called the training, the pilot training. For example, before I transmit data from transmitter receiver, I first send a pilot, P-I-L-O-T, pilot. What does it mean? Pilot means that is like the test symbol, test data, which is known for both transmitter and receiver. For example, I transmit signal 1, okay, symbol 1, for example. I transmit 1 here from channel and then to the receiver. If the receiver get the signal as also 1, okay, it's perfect. No noise, the channel no fading, 1 and 1, that's perfect. If it's not 1, it is, for example, some other thing like the 0.9 or 0.98 or 1.2, then you can imagine the channel may have some noise and also have no fading or coefficient H. That will change the symbol I transmit. So what I do that based on the received signal and the transmitted signal, and then I can estimate the channel. So I can use a page to explain the training method. So this is like the, what happened? Yeah, this is a channel which is we don't know. I want to estimate the channel information. So firstly, we transmit called x equal p called the parallel symbol, which is known for both transmitter and receiver, and we got y. Generally, we say we have the model hx plus noise. If we consider one-to-one, not minimal, for simple example, okay? So h you don't know, n you don't know, right? So you say I transmit signal x, and then I got signal y. Because I'm at a receiver, I can observe y value. I know the y, I know x, you know that? So then I could estimate h. So that means, because noise is, you can never know this exact value of noise, but you know the distribution noise, right? So that means we can use, we can want to minimize the noise power so that we can try to find the x. For a simple example, is that we can ignore the noise. That is called the least square estimation method. We say the h is just y over x. So that would be a very simple example. Okay, so we assume that the noise could be ignored. If for the little noise, then we just use it. We know the y value, observation. We know the parallel symbol, y over p here. So then we can estimate the channel. So that is called the training method. You have also other methods, like the minimum mean square error estimation method, ML estimation method. So this is the only simple one, okay? I just want to tell you, we don't need to discuss the method because there are many algorithms to estimate the channel. But I want to let you know the procedure. Once you get this channel, how you can get it to send back to the transmitter. So from here, so we call the CE. CE means the channel estimation. Then you can get the channel. Because it's an estimate, we can add a hat. So then from y and also from the training symbol p, right? Because you know that this is not the real data, this is a test. In the test process, we know, okay, the signal x is equal p, because this is called training procedure, right? Training phase. So we know the p value, we know the y value, so we can use some estimation method, algorithm, to estimate the channel h. Once you know this h, I can change the color, that is, you need to send back this knowledge h to the transmitter side. So that is called the channel feedback. Because remember, so the right-hand side is called the receiver, right? As a receiver, you go to observation, the measured value of y, you know the palette, you estimate the channel, and then you need to send this channel information, the estimated value, back to the transmitter side. Okay, that's not easy one, because that will require additional channel, additional bandwidth, additional communication channel, right? So the forward channel is like the data link. The feedback channel is like the specialized channel. That means you need to get the channel information back. So in real world, so you do not send back the real value of the h hat. You send back the Q of h hat. What's the meaning of Q? Q means the quantized version. For example, h hat is equal a complex value. For example, h hat equals 0.23 plus 1.58 j is a complex value. You cannot send the real value back because it takes a lot of the story and memory and occupy the bandwidth. Usually we only send a number of the bits. That means we quantize the value. We only, for example, we use the 6 bits, and then we quantize this range by the 6 bits, that is 2 to the power 6, 64 different level. That means we divide this range by 64 different equal division. We round that value to the nearest level. This is like very simple case we send from called the passcode modulation, if you studied that before. Right? We do not send the real signal, we send the quantized, the bits. Okay. So the quantized channel feedback will be used to store the data of the channel and send the channel information back to the transmitter. And then as a transmitter, we see this is called CSIT. Channel state information at transmitter. That's called the CSIT. So usually this CSIT is not easy one. It will require additional channel for the feedback and also require the quantization and also the transmitter side. Once you dequantize, so you actually that is definitely each hat is not equal to each hat because you will lose some resolution. That means called the quantization error, right? You quantize the value, then it's definitely not equal to the true value of each hat, and also not equal to the true value of the channel, because you have the estimation error, you have the quantization error. So that means when you send back the data, the channel to the transmitter, so that QH hat is totally different from the true value of H from these steps you see here. So that is channel state information at the transmitter. So only in that scenario you say, okay, I know the channel. So once you know the channel, you say, if you know the channel, then we can use SVD of the channel matrix to perform the precoding. So that's why here, when we say, okay, we can use the transmitter precoding, actually it involves many steps to do this on the right-hand side. When you say transmitter precoding, that requires you to know the channel knowledge at the transmitter side. That requires you to do the channel estimation, channel feedback, so that you can use, say, I know the channel at the transmitter, I can use the precoding, right? So that is, we call that channel information is known as a transmitter, okay? Only under this scenario, CSIT, we know the channel information at the transmitter side, we can apply the transmit precoding V. In that scenario, we can get the channel model 7, or this one. Remember, all these results are based on transmitted precoding. Without precoding, you cannot get equation 7, right? So once we know the CSIT, we can use the precoding. V, we can get equation 7, we can get this matrix, or this equation, right? So that means we can decompose the channel into the number of the parallel Gaussian channels. And then with the capacity, simple, we just sum all these parallel channels together. That is, we want to sum of the CI. For each, look at this one, each channel is just an AWG channel with a lambda I. And then we take the sum of all the channel capacity. So the summation of the log 1 plus SNR, that's a lambda I square PI over the noise power. So that is for the one channel. And you take the sum together, that is the minimal channel capacity. So you may wonder, this result is totally different from what we did before, like equation 6, right? Now you say, I got equation 8. It's also called minimal channel capacity. But this one is much simpler, you see, right? Because this channel now is a parallel Gaussian channel. So what you do is just take a sum, because channel capacity is just a sum of each channel, individual channel. It's exactly what we did for the parallel Gaussian channels. I do not have that slide 8. Where is the slide 8? Let me see. Lecture note 8. Okay, here. Yeah. This one. And you can make the comparison of this one. Look at that equation, this one. Yi equal lambda I xi plus wi. Wi here noise. I from 1 to rank of each. You can consider the 8 rank from probably 4, 2, 3, something. Okay, it's like this is a parallel Gaussian channel. The only different line in here, you have the constant, lambda I, right? Then xi, this is signal multiplied by the lambda I, corrected by the noise, you get yi. And what's the capacity that's given by here, right? And do not forget this lambda I squared because you transmit the lambda I xi in the beginning, right? So that's the capacity. Now the difference between this one and the previous one is huge. Why? Because here you see this is determinant, but this one is not a determinant matrix because we know this channel can be diagonalized like this one. So that's why the determinant of the diagonal, okay, that's obvious. That's just the sum of the log equivalent. However, remember we have the assumption for this result. The assumption is that CSRT. It means that if you get the additional information, like the CSRT, you can do something better. You can do the pre-coding, then you can diagonalize the channel, you can remove the interference so that you can increase the channel capacity. In other words, equation 8, this value, capacity value, is higher than the value given by the equation 6. Okay? Why? Because for the equation 6, the channel is also given, but it's only known at the receiver side, not known at the transmitter side. So that means at the transmitter, we only transmit X, not a Vx, because we don't know the V. But now, later we say, okay, you know the V, you know the channel at the transmitter, so we can do better. We can do the pre-coding. And then we can transmit Vx, not X. Vx better, so that we can make the channel compatible like this one. So it means that equation 8 is better than equation 6, right? 6, in terms of the capacity value. I remember that we have the project to ask you compare the channel capacity results for the different scenario. So this is one. Once you know the CSRT, you can do something better. You can make the capacity higher by doing this thing. Okay. And also, this is also very similar to the power allocation problem. You say, we want to maximize the capacity of how much power should I allocate for different channel, P1, P2, P3, what's their value? So remember, lambda I is a constant, sigma is a constant. So the only, I think here is quite simple. You just absorb the lambda I square into the denominator, so that is a sigma square over lambda I square. You regard this ratio as new sigma I square, new noise variance. So that would be or called Ni. Ni equals the sigma square over lambda I square. Then you will get this equation. There's no difference, right? Pi over Ni. Ni equals sigma square over lambda I square. See? That will be the same as this one. Then what's the solution? It's given by this. So that means you can solve this equation 8 also using the water filling solution to get the answer. So in other words, if you have the large lambda I square, you will have the smaller value of Ni, right? Then you can allocate more power. So that's obvious. The better channel get better, larger power. So therefore the CSRT. Okay, so another scenario, if the CSI not known as transmitter, you cannot do the pre-coding. What you do is that you either just transmit like this way, randomly, or you can say I transmit the power evenly, allocate the power evenly, because I don't know the best power allocation. I have no information about the channel, right, before I transmit. So I only evenly allocate the power across different antenna. So I can get input covariance metric like this way. I substitute its value into equation 6. Okay, so then you can get this answer. So this one definitely is much lower than equation 8, because uniform, that means you have no additional information. So that is the only case you can do that. But if I get more information about CSI, I have a better solution. I have a better option, right? So that is a comparison between two different power allocation schemes. Okay. So next, I would like to introduce different channel capacity definition. Previously, we talked about the channel capacity, especially the equation 6. That is a general result for a constant channel. Remember the first assumption, that is constant. H is given and constant, fixed. So now we want to relax this constraint assumption. How about the channel is fading? Here, the channel is fading. How can we do that? Okay, look at equation 6. This result is a capacity for a constant channel of H. But now you see H is now varying, H is fading. That means H follows some distribution of the random variable. So what you do is that you can take the average or expectation of this result for different value of H, right? So that means we take the expectation of capacity result for the different value of H. That's called ergodic capacity, you see? Expectation of H. And this one is just the equation 6 inside, right? Now you say H is varying, so we should take the average. I mean, when you take the average, I mean the statistical average. It means that you need to know the distribution of H. Then you can take the statistical average. So you know the statistical average. That means if I want to, just a second, I don't know, it does not work. Okay. I want to take the expectation with of capacity, and the capacity there, that equation 6. You remember that equation says that's a log determinant of the sum H, right? And then now C, if you say H is not constant, then C here is varying. It's distributed in some ways. Then we need to take the average. So then you need to know the distribution, the C here, and the distribution of H, and then DH. So that is the expectation, right? You need to know the distribution of the channel, and then you take the integration of the C. C, that is the equation 6, right? Definitely C includes the term of H, and then take the integration altogether. So that is a statistical average. So that's called ergodic capacity. So another method, you don't need to know calculate exactly. You just do the simulation by MATLAB, by programming. You just generate, firstly, you fix the constant channel coefficient, then you can calculate the exact formula result of the capacity value from the equation 6. Next, you change the channel coefficient, right, randomly, following the distribution of H. If H, for example, is a Gaussian, it's a Rayleigh distribution, it means that this H value is complex Gaussian, then you need to generate another realization of H value from the complex Gaussian, and then you get this new value of C from equation 6. And then you do again and again and again, million times, you can take the average overall. That is called ergodic capacity. You can see here, I get the different settings of MIMO. You could consider one antenna, one receiver antenna called CISO, two transmit antenna, one receiver antenna, one transmit antenna and two receiver antenna, finally two transmit antenna and two receiver antenna. And also for the different SNR dB settings, for example, 10 dB SNR and 2x2, this one square, you can get exact answer capacity value. That means that for 10 dB SNR, two transmit antenna, two receiver antenna, what is that channel capacity on the average? Okay, we can see this one, 10 dB, 2x2, is given by here. This value is around, let me see, 5 bits per second per hertz. 10, 9, 8, 7, 6, 5. This is around 5. Is that 5? Okay. So how do you get that? That means you need to generate 2 by 2 matrix of the channel randomly, and then you substitute this result into equation 6 to get the channel value, capacitive value, and you do that iteration many times, million times, take the average. That will be 5. Okay. For the 10 dB SNR, remember 10 dB SNR. Because equation 6 relate to the SNR, 1 over sigma squared, that's the SNR, right? So, and then you also try the different value of the SNR. If you have high value SNR, look at that equation 6, capacity will be larger. So that's why it is increasing. And also, you can say 2 by 2 antennas, it always has higher capacitive value of 1 by 1 or 2 by 1. You can, for example, we could say for 30 dB, this value is around 9 or 8, right, bit per second. But look at the 30 dB, this one. For square, that will be, this is 10 dB 20, that almost 20, but not 20, around, almost double the value result of the 2 by 1, 1 by 2, or 1 by 1. So in other words, if you have more antennas at both terminal receiver, the capacitive value definitely will be larger, right? But why this 2 by 2 is double? Because this is rank. Remember here, if you rank of each, rank of the channel depends on the minimum number of the antenna. If the 2 by 1 or 1 by 2, the rank is 1. Look at the matrix, right? 2 by 1 matrix, 1 by 2 matrix, the rank is 1. 2 by 2 matrix, its rank is 2. So rank is 2, that means you can get virtually 2 parallel channels. If you have only rank of 1, it's still 1 channel. So that's why they have the difference. For the 2 by 2, it has a higher capacitive value. I remember one project question asked about this similar question for this one. Okay. Second definition is regarding the outage capacity. Outage capacity, so outage means that sometimes that when the transmission rate is beyond the capacitive value, we call that outage. Remember that in the capacity lecture, we give the Shannon's theorem, but we did not prove it. We say that if the transmission rate is smaller than capacity, we can always get almost the error-free transmission. On the other hand, if the transmission rate R is larger than the capacity, we cannot guarantee the error-free, right? So then we say that is outage. The outage that is defined that when the transmission rate is larger than capacity, so that is a disaster because the capacity is, for example, 10. You want to transmit 20 beyond the capacity, then you will get error anyway, right? So outage capacity, that means that, okay, we remember the C here, if from the equation 6, you see that is capacity value. But if we now, this is for a given channel, right? This is a condition for the equation 6. For a given channel, you got equation 6. But now, for the varying channel, so CH for feeding channel, then CH here is not a constant. If you look at equation 6, every time you substitute in the different value of H, you get the different value of H, C. So if I, for example, if I have a different value of H, then CH may be different, I don't know, like this one, because it's random. Sorry, I should show the whiteboard. Sorry. Okay. So that means the C here is the equation 6 is for a given channel, but for feeding channel, CH here is a variable. So that's why I say this is CH. You see, if we have different value of H, CH will be different, all right? Because it's random. H is random, CH will be random from equation 6. Now, what is the outage capacity? Outage capacity, that is if we say, I use different color, I set a bar. I set a horizontal bar, and this value is a constant called C alpha. I say that, what's the meaning of how many chances this CH can be above of this bar? I will say that is probability of outage. That is, firstly, you see CH is larger than C alpha, so that is called outage, because that is bar. If you over the bar, so that will be outage, then I want to know that's the probability equal to alpha. And alpha here could be say that the 99%, let me see, this is 99%, yeah. Or 91%, so I want to find that bar. For example, this CH, I say 99%, this CH is above this bar. Definitely the bar is higher, the CH will be better, right? Because that means on the average, you have a high capacity. 99% of the time, your capacity value is larger than 10 or larger than 100. Definitely higher bar is better, because a high bar means that you get a high capacity, right? So that means usually we set up we want to find out the bar, C alpha, when this probability equals 99%. So firstly, CH here is the random variable. You know, H is random variable, then CH will be random variable. And it's a random variable larger than a constant, so actually we say that is called outage. And then we want to calculate this outage probability to be the 99%. So that's called outage capacity. So here I can give you, there is a figure, 99% capacity. You see here, for different, you just look at one dot. For example, 2 by 2 square, and 10 dB. 10 dB here around here, this one. So this capacity value, you see 10, that will be 12 or 13 around, beat per second per hertz, right? And for other settings, it will be smaller. So it means that the bar for 2 by 2 is higher than the 2 by 1 bar. For the 99, under the same 99%, then on average, then 2 by 2 will be higher. So I can illustrate this different thing. Whiteboard again, you see here. Okay, so first I draw the 2 by 2. 2 by 2 stage may be here. This is stage for 2 by 2. 2 by 2 means 2 transmit antenna, 2 receive antenna. Okay, this is H, this is CH. No works. What happened? Okay, and then I want to change the colors, talk about the 1 by 1. 1 by 1 may be here, like this. You see, okay, they are both random, but most of the time the black is below the red one. So that's for 1 to 1. 1 transmit antenna, 1 receiver antenna. If we set a bar saying that, okay, for the 99% of the red one, so it maybe is given by here. 99% of that is this one. So that is for the C 99% for 2 by 2. You can say the red one is above this blue line for the 99% of time. And for the black, I use different color. Let us see, green one. So this is 99% of the 1 by 1. You see, for the black one, then it over the black, the blue, the green bar for the 99% of time. Clearly, the blue bar is above is much higher than the green bar, right? Because it has the more antennas, the capacity will be higher. So we use this outage capacity to show another difference of the comparison of different antenna configurations. The last one is called outage probability. Outage probability means that if you have the capacity, the rate larger than capacity, as I just mentioned, you have the outage, and then we need to calculate that probability of this given rate. Okay, so that is, for example, we give the constant rate 2 bits per second per hertz. Then we substitute in this equation, the probability C is smaller than 2. That is called outage probability. So you say 1-to-1 had a very high probability of outage because why? Because usually the C value for 1-to-1 is, let me see, outage probability is higher because the C value for 1-to-1 is very small. Then the small value is smaller than 2, that means it may happen frequently. That means the outage probability is higher. But for the C 2x2, the C value is higher. If this is higher, then this one is smaller than 2, so that probability is small. So that's why you can see for any given SNR value, the 2x2 has the smallest outage probability. That means it has a small chance of to be outage. In other words, most of the time 2x2 can support the high data transmission. And for 1-to-1, you see the probability is around 10 dB, around the 0.3. That means 30% of time it can support the data transmission 2 bits per second per hertz. 70% it does not support it. It is in outage for 1-to-1 antenna. So that also shows the different metrics. Okay, so that is the different comparison for the MIMO channels for the feeding coefficients. But we mainly use the simulation. We did not do the exact derivation analysis. But there is formula, very complicated, so we do not talk about in the lecture note. So we only show the simulation result. You see, this curve is not very smooth because of some of the simulation errors, right? Yeah. Okay, so that is about the MIMO. We just talked about this. I think we still have a bit of time. I want to introduce some concept of diversity encoding. And also, I think that's a very good timing. We talk about this curve with this outage probability. Look at this one. I just talked about the outage probability, and it's always decreasing function in terms of SNR. So for sure, you have a larger SNR, your error will be smaller, right? That's true. But look at this decaying speed. It is very different. For this one, okay, slope not too deep, right? But this one is fast decreasing because if you look at like the hill, so that's a drop down very quickly, right? We call it the descent, or the slope is very steep for this one. How we can characterize, model this decaying speed, the trend? We use this one, GD, diversity order. Look at this one. The error rate can always be written as this formula. Because this is error rate, you see outage probability is like the error rate. The x-axis is SNR for dB. And this curve can be written as a general formula of the constant times SNR times minus GD. GD is the diversity order, or called the slope of this error rate curve. If you have the higher value of GD, you say SNR minus 2, SNR power minus 3, you will have quickly descent of this curve. So the GD means this is a decent degree. And the GC here is coding gain. Coding gain means that is a parallel shift. If you have different 2 times SNR or 5 times NR, so the difference lie in the, if you take the log, that's a log of 5, log of 2, plus SNR, right? So that is only the shift of this log, of this curve. So we say the coding gain, look at this curve, it's just the left or right shift of the curve. But GD here, double order, show that the speed of that decreasing or slope of that curve. You see here 2 by 2, this one has the largest order of 2. And this one, not 2, this is 4 actually. So this can be explained later for when we talk about the, I think in spectral coding we talk about this one. You see, 2 by 1 and 2 by 1, 1 by 2, they have the parallel, right? 1 by 1 like this, 2 by 1, 1 by 2, 2 by 2. So actually there are 3 speed values. For the 1 by 1, the decreasing is just the 1. That is SNR minus 1. Let me see, can I write here? I probably cannot, right? Let me write in the whiteboard again. I can better show you the meaning. Okay. Just wait a second. So look at this this figure I will draw here, okay? So this one is 2 by 2. This one is 2 by 1. And this is SNR. This kind of the error rate. Outage rate or error rate, right? Look at this one. Okay. For this one, what happens with their decreasing speed? This one actually is SNR power minus 1. This two is SNR power minus 2. This one is SNR minus power 4. So that's why you say when we increase SNR value, so 2 by 2 antenna decrease error quickly. So that's why we prefer more antenna, because we can reduce the error quickly, right? You may wonder why it is power 4. So actually this is decaying speed we call the diversity order, SNR power minus JD. JD means the diversity gain. We just talked about today. Where's the slide? Here. JD, where's STC? Let me see. It's here, JD here, right? SNR power JD, okay. So JD value, you can see this is 1, this is 2, this is 4. Actually, later we can prove JD is equal to the multiplication times the multiplication of the number of transmit antenna and number of the receiver antenna. That's MN. So that's why you say 1, 2, and 4. 2 by 2 is 4, because it's related to the multiplication of number of antenna at the transmitter side and the number of antenna at the receiver side. So that is, we can prove it later, not now. Okay, that is this one. Okay, so let's continue. So that means for any system, we usually evaluate the system by the error rate, the gain, and diversity gain. Okay. There are many methods we want to decrease error, right? For sure, we want to increase the diversity gain so that we can decrease error. So there are many methods. One method is called the time diversity. Time diversity, very simple one. I mean that we transmit data multiple times. One time we may get lost. We can have another copy, another time try. So that's like the repetition, right? Time diversity, simple. Today we repeat, tomorrow we repeat again, and the day after tomorrow we repeat again. So anyway, even you lose the information today, probably tomorrow you can get it. So this is like the time diversity, but it's very low efficient, right? So that means for the same information, you need to transmit multiple times. Or frequent diversity. We transmit the same thing through different channels. Even you lose information from one channel, I can get another channel, right? So that's called the channel diversity or frequency diversity. Another option is that the space diversity or antenna diversity, like what we just did for the MIMO. If we transmit the same information from different antenna, you will see we will also get the redundant information. If we lose information from one antenna, we still get another channel from the second antenna. It's called space diversity, right? So like you got the 2 ears, right? You got the signal coming from 2 ears. Even you cover one ear, you still can get a signal from the other ear, right? So that means it's like the redundant. It's called the receiver diversity, okay? That's good. And the receiver diversity is a good thing that it does not cost your time, does not cost your frequency. It just costs you some space. You need to get the 2 antenna or more antenna, right? You don't need to transmit multiple times. You don't need to transmit multiple frequency bands. So that's why we prefer the antenna diversity. For antenna diversity, so there are many benefits. Firstly, it has, as we said, it just needs to implement multiple antennas, and we don't need to cost the time and frequency. And also, you could increase the transmission rate through multiple antennas. As we said before here, you see this is the capacity value, ergodic capacity, this one. If you have more antennas, your rate is higher, right? Look at this equation, look at this simulation. Also from the equation, we get more channels. Look at this one, more channels, and then we can get more higher capacity values. So that means you can get a higher transmission rate, you can get a better performance of the error rate. It means that you have the higher value of the antenna, you get a lower error rate. That's true. That can also be applied to many feeding channel. There are many, this one I think more advanced. You don't need to deal with that. For antenna diversity, there are 2 methods, but actually we use both. Either that just use multiple antenna at the receiver side, or called receiver antenna diversity, okay? And the other one is called transmitter antenna diversity. That means use multiple antenna at the transmitter side. But in our MIMO, we use both, right? Look at this one. We use multiple antenna at both transmitter and the receiver. Then we explored antenna and transmitter antenna diversity and receiver antenna diversity. The both, okay. So then we come to the spectrum coding. Just to give quick definition, then we can go to one example to let you know what's the meaning of that spectrum coding. Spectrum coding is one approach to achieve this transmitter diversity and also receiver diversity. It transmits a signal through different antennas and different time slots. It has a number of the benefits, so we can explore that later. But first, we need to investigate what is spectrum coding. I can give you an example, but we do not go to the detail, probably after break. So for spectrum coding, look at this one example. This is 2x2 code word. Okay, this is simple for 2 antenna only. For multiple antenna, that we need to change story. Okay, for 2 antennas from transmitter side, you see, we have 2 row, 2 column. I use time and space. It means that the first column is called the space dimension 1. That means the first column will be sent through the first antenna of the transmitter. The second column will be sent through the second antenna of the transmitter. And the first row means that they will be sent at the first time slot at the same time. This second row will be sent at the second time slot at the same time. So if you want to see this example, that's what I just mentioned. So this is T1, S1 was sent. At the same time, T1, S2 was sent from second antenna. Okay, and then in the second time slot, minus S2 conjugate, you may argue, what's the meaning of why do you want to send minus S2 conjugate? We'll talk about that later. I just say you want to send a different signal, okay, through the first antenna at the second time slot. At the same time, you send S1 conjugate from the second antenna at the same time. Okay, you can get, at the receiver side, you could get one antenna or multiple antenna, but here I only illustrated one antenna, but we can extend, we can get more antenna, no problem. I just want to simplify the analysis. I just draw one antenna. You can draw another receiver antenna. You can get R3, R4. That's easy, okay? And then you say you use 2 time slots to send the signal, and then at the receiver you get the 2 receive signal, all right? So that is called space-time coding. Look at the transmitter side, you use different antennas, different time slot to send a code matrix, this one. This is called code matrix. But this requires some careful design, but I have not told you how we can design it. I just told you, okay, this is the code word C, send it, okay, through a different antenna, different time slot. That's called space-time coding. And then after break, I think we can have a quick break. Then we can come back to the detail of space-time coding, how we can design this space-time coding to explore the better benefits, okay? We can take a short break, okay, 10 minutes at most, okay? And then we can come back to see the transmitted coding and decoding. Yeah. Okay, so we can get started now. Yeah, we just talked about the spectrum coding. Let's go back to my coding side here. I think that we have the project regarding the spectrum coding, especially to calculate the capacity automotive coding or the area automotive coding. So there are the project you may need to do. I remember that a few days ago I received the project submission already from a couple of students. So they have done the job very quickly and submitted a report before I give the lecture about the automotive coding. So let us see automotive coding. 10 minutes ago I talked about the format of spectrum coding, right? That means you transmit multiple information symbols through different antenna at different time slots. That's called spectrum coding. But I have not told you about how we can construct this spectrum coding. So the first example is called automotive coding. That's due to the inventor of the coding called Alamotti. So Alamotti, it's a legendary person. He does not have any PhD degree. He's an engineer. I remember he studied in the Waterloo, University of Waterloo somewhere, and then he became the technical staff in some company, probably Bear Lab. And then during that time, the MIMO system became a candidate technique for the future communication in 1995 around. And he works on this technology as an engineer because he's not PhD, right? He didn't think about the problem from theoretically. So I'm not sure if you know some PhDs, like my PhD students, they're usually worrying about to publish papers to get a degree, because PhD is totally different from the master's. You have to do the work this had not been done by most of the people in the world. You have to do something which is unique, and maybe you are the first person and only person that you can get some original result and publish the paper. And Alamotti, good thing that he's not a PhD, so he can think about the problem practically. He gave this idea of this code, but he has no theory. And when I heard some story about this paper submission. This journal is GSEC, Journal Select Area in Communication, a top journal in our area. And when he first submitted the paper to the journal, it got immediate rejection, and then he revised and resubmitted again, and then get some attention. In the beginning of this paper, if you read, you can download this paper and read it. It's quite simple. It's like your project. Yeah, you look at all the equations, very familiar, very simple, no advanced theory, no some theorem, no proof, just saying, okay, I designed the two antenna system, like what I just showed you. I transmit this, even he did not show this matrix. He just showed the equation by equation. Probably he's not very good in the matrix. He does not show like the matrix form. Okay, he showed the equation by equation, and then finally he found out it's good code. And then he stops because he has like the visionary ability to extend the result to any number of antenna. But nowadays, we know that this coding can be applied to any number of antennas, but that's all due to the contribution of the mathematician, because most of the coding were done by the mathematician, not by our engineers or the wireless communication engineers. So automotive code, you can see this code is very simple, right? You transmit S1, S2, and then in the same antenna, you swap the position at S1. Not only that, you transmit minus S2 conjugate and S1 conjugate because you assume S1, S2 are complex. If S1, S2 are real, actually you transmit S1, S2 and then minus S2, S1, right? Just the swap and the minus sign. You may wonder, why do I need to add minus sign there? Very unusual, right? S1, S2, minus S2, S1. But if I tell you that a Hadamard matrix, probably heard about it, Hadamard matrix. 1, 1, minus 1, 1. You know that? You have two column vector, 1, 1, 1 minus 1. These two column vectors are orthogonal to each other. Is that right? 1, 1, 1 minus 1, 1, 1. They are orthogonal vectors. They are called Hadamard matrix. And this is orthogonal. From here, again, S1, S2, minus S2, forget conjugate. Okay, we'll talk about the real. S1, S2, minus S2, S1. It is also orthogonal matrix of the symbols. Why is it good to use orthogonal? We will find out that later. Okay, so orthogonal can be applied to any dimension, but Alamotti can only think about the 2 dimensions. On one side, you can say, okay, Alamotti is smart. Okay, think about this code, but probably you don't know that its impact. So its impact is very huge. Even he didn't know that in the beginning. And I can Google for you. You can see this his work, a simple transmitted tenor diversity technique. Let me see. Control C. Use Google. Let us see these papers. Where is the paper? Here. Where is the citation? I think I better use Scholar Google. Scholar Google. Okay, these, you can download the papers. It was viewed 36,000. It was cited almost 10,000 times, but in the Google Scholar, it will be much higher than this number. Let us see, cited by, you see the number, cited by almost 20,000. What's the meaning of that? It means that this paper was cited by almost 20,000 papers, 20,000 papers in wireless communications. You can imagine how many papers were published each year, right? So 20,000, this is the number one, I think probably number one in engineering, in engineering field. Not only limited to the wireless communication, but for all the engineering field. So it's the highest number of the citation, 20,000 citation. And in fact, this code has been adopted in the standards of the Wi-Fi for the 2 antennas. You can see, you can Google this, in different standards for this one. And if you have more interest, you can Google the Alamotti himself. Let me see. I think he got his own company now. Yes. His contribution is just some block code, these papers. Let me see. Where did he did this job? Let me see. He joined. Vodafone, the research director of Vodafone. That's later, and he worked out this work by join this company, now AT&T, correct. He was working with AT&T as a senior scientist, and he invented this 2x(n). Today I'll show you 2x1. Actually, it can be easily extended to 2x(n). Today we call the Alamotti code. And this is called the best of the best of 50 years of communication research papers. And he got also a number of the significant research award, etc. Okay, so and all the big names that he worked together, they are all the professors, like the Wahid. He's the Harvard University professor later, because they were colleagues together in the same office, in the same team. Robert Cardbank, I think he's the Dean of Engineering in Duke University now. And Hamid, he's now also professor in the University of California. So they were in the same group in the AT&T Bell Labs, and they invented spin block coding extended to the MIMO systems. So that is a huge breakthrough in the wireless communication. Okay, so let's come back to see the why it's useful and simple. I strongly recommend you can read this paper, download the paper and read this paper for details. I'll give you a very simple explanation. Okay, so let's say we transmit the S1, S2 simultaneously at same time slot. You can get R1, R2, right? From this model easily. R1, that means equal H1, S1 plus H2, S2 plus noise. R2 is H1 times minus S2 conjugate plus H2, S1 conjugate. There's no question, right? Okay, secondly, I put in a vector. R1, R2, I put it in a vector form. So you can see I can rewrite this equation as this one, S1, S2 times H1, H2, right? This column vector of H plus node vector. Can you see that? And for the second row, you can also get the minus 2 conjugate times H1 plus S1 conjugate times H2, like this form. Okay, this is automotive code matrix times this one. So far, okay, it's easy, right? It's just a simple signal expression. Secondly, I just do a minor manipulation. I change R2 as minus R2 conjugate. That's simple, because at the receiver side, you observe signal R2. I just add a minus sign, take the conjugate, nothing changed. But when you change that, mathematically, on the right-hand side, you get this form. Compare the equation 1, the first row does not change. H1 times S1 plus H2, S2. But second row, you can say that will be changed because you have the minus sign conjugate. That means that will be H1 will be H1 conjugate times S2 plus S1 minus H2 conjugate. So equivalent to say you put this one, second line, into minus conjugate, you will get the second row here. So I just rewrite that matrix as matrix H times S. So far, it's still okay because you have not seen the detail. Why? What happened? What's the magic? Magic. No, not happening so far. I just redo the signal representation. Next, I think that will be magic. Look at the matrix H. You got H1, H2, minus H2 conjugate H1 conjugate, right? Remember this? This H. I called H times S plus noise, okay? And next, H Hermitian times H. What happened? Look at this. H Hermitian, I can add a whiteboard to rewrite so that you can see clearly here. H equal H1, H2 minus H2 conjugate, H1 conjugate, correct? So now I want to rewrite H Hermitian. H Hermitian means that you first take the conjugate and then transpose. It means that H1 conjugate, H1, and this is H2 conjugate, and minus H2, right? Transpose and conjugate, yeah. And then you want to calculate H Hermitian times H. These two matrices multiply each other. So what happens? You can say H1 conjugate, H2 conjugate, minus H2, H1 times H1, H2, minus H2 conjugate, H1 conjugate. And this is just the 2x2 matrix multiplication. I can tell you, you will get this form, H1 squared plus H2 squared. And this one is the same thing. And this is 0. The over diagonal is 0. That will be cancel each other. You can easily check. The first row times second column. H1 conjugate H2 minus H2, H1 conjugate. That's 0. This one, second row, first column. H2 conjugate H1 minus H1 times H2 conjugate. 0, right? The main diagonal is the same thing. So that's why we get this form. You see, it's A, that is H1 squared plus H2. This is called the norm. H1 square, norm square equals H1 times H1 conjugate. Because it's complex, okay? So then you can say A, just the H1 square plus H2 square. So that's why it's A times identity matrix, right? Look at this Y, this one. It's like this one, A, 1, 1. And A is just H1 conjugate, H1 square plus H2 square, okay? It's given by this. If this has such a property, what does it mean? Because you got R equal HS plus noise. Next, at the receiver side, remember here, this is your observation, R1 minus R2 conjugate. I know the channel information, I know the H1, H2, I can get this matrix. Next, I want to do is that on the left-hand side, I multiply H Hermitian on the both sides equation. So then you say H Hermitian times R hat on the left-hand side times left multiplying H Hermitian of equation 2. You got this one. On the right side equation, you get H Hermitian times H S plus H Hermitian noise. You got this one. And this one doesn't matter, it's still the noise. We call the new W, the noise. But look at this one. H Hermitian times H is a diagonal. It's AI, diagonal, which is A diagonal times S. It's just AS, right? A times signal vector. So then you say vector S is S1, S2. This is Y1, Y2. So it can be split each other. So you can get Y1 equal S1 plus W1, Y2 equal S2 plus W2. What does it mean? The two signals are separated from each other. Look at the signal model, look at here. In the receiver, you got R1, R2. No way to separate because S1 and S2 are mixed together. It's really hard to decode. But now, our receiver side, once we multiply this equation, the matrix H Hermitian, we can separate the signals, the S1, S2, right? It's like the parallel channel, 2 by 2 like the parallel channel. You don't need to use SVD now. You don't need the channel knowledge as a transmitter, like the precoding what we mentioned before. You only left multiply the equation, the matrix H as a receiver, not as transmitter. So you can get the same result, parallel channel. So that is the big result. You may say how big the result is. Because you can simplify the system design. You don't need the channel feedback. Previously we say we need the channel feedback so that we can design the precoding vector V so that we can perform SVD to make the channel to be parallel. But now you don't need to do that. Just use automatic coding. A receiver, you can do the parallel. You can separate two signals. And then in the decoding, you just make the detection of a signal one by one, separately. I detect S1, and then I detect S2 by this equation, the minimum, the ML decoding, or minimum distance decoding, separately. So that means the ML detection automatic code can be decoupled into two parallel decoding. So that one method, that means the low complexity decoding. Secondly, it does not need the channel knowledge as a transmitter. No channel feedback is required. And also, I don't have time to go further today, but I can tell you that another good news about the automotive code is that it's a full rank. Because it's orthogonal code, and it can get the highest diverter order, and also it can get the highest transmission rate. So this will be detailed next week. Okay, I'll just give you a summary of the benefits of automotive code. So, and also for other number antenna, we can also go further. So simple thing that I want to, because due to the limited time, I have to summarize. That is, automotive code, although looks very simple, it can give us some of the new horizon of the design. You don't need the channel feedback. You can do also something better. You can do the decoding very simple. You can also increase, you can achieve the diverter order 2 because its rank is 2. And it is also orthogonal code. Orthogonal code because the channel you see here is orthogonal. Why this channel is orthogonal? Because this channel is due to signal encoding block so that this channel is very special. You see the channel is also like the automotive code. due to allomorphic code, we can get this allomorphic form of the channel, which is orthogonal. So that all the benefits of the allomorphic coding. Okay, I have to stop here. And next week, we can go further to discuss the MIMO error analysis. That's not easy one. I think that's a challenging one. Probably we take 1 hour to talk about that one and also other code. And further, we have another 1 hour more to talk about the of them and the mom of them. So next week, that will be week 10. Okay, that's it. Yeah. Thanks. Wow, mad equation. Okay, yeah.
我想问一下，你下学期有没有课题，就是开课？